5 minutes, something like that, right?
Yeah.
Okay, so I just try to share my screen.
45 minutes and then some question answer.
Okay, okay.
Sometimes for question answer.
So you see my screen?
Yeah, I can see your slide.
Let me just choose. How do I make it? Full screen mode. Okay. So well, thank you for the introduction. So yeah, I'm talking you from Paris. So I'm a postdoctoral researcher in a laboratory for informatics in Paris. Laboratory for Informatics Paris 6. So it's in quantum information team. And the title of my talk will be Device Independent Certification of Quantum Resources. So that is somehow broadly have been my main interest during my PhD and my 2 postdocs. So I tried to tailor a talk a bit like as I was asked to students so that it could be understood well. And in principle, well, I don't know how I could see if you have questions during the talk, but there is some way interrupt me and it's okay. So just let me understand how to, yeah. So, well, the main topic of my talk would be quantum certification, and well, I start with this phrase like told by Richard Feynman that nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. So that was somehow the first intuition of importance and usefulness of quantum theory for various problems in computation, and we also know from other sources that quantum was important for developing information theory and other fields. And indeed, we know that quantum provides advantage in various different tasks. So, for example, the most important, well, not maybe most important, but very widely known is quantum advantage in quantum computing. So for now, we know that quantum algorithms have, or we postulate that they have higher efficiency in solving problems. So we know that, for example, Shor's algorithms can more efficiently factor primes, and we don't know classical algorithms that can do the same. So then if we talk about quantum communication, like, for example, in cryptography on sharing of a secret key, in classical cryptography, like security of the protocol was always based on some computational assumptions. And in quantum, if we define a quantum key distribution protocols, like we have information theoretic security, that means that like basically the laws of physics are responsible for the security of our protocol. We are not assuming that some problems are mathematically difficult to solve. And then also like important usefulness of quantum theories in sensing, where we have better precision limits, so we could make more precise measurements, and like this is encompassed by quantum Cramer-Rao bounds. This is all nice when we talk theoretically and when we have our quantum resources, quantum states, quantum measurements. But then, as we know, like the quantum resources are very fragile and like they are difficult to control. So very often noise becomes detrimental. So for example, in quantum computing, noise and decoherence counteract this efficiency, and when they're taken into account, like classical machines can perform as well as quantum. And this is behind all these efforts to develop fault-tolerant quantum computing. In quantum communication, we phrase the protocol, for example, for quantum key distribution that has some level of security. But then if you take into account, for example, detection and transmissions losses, like eavesdropper might use these effects to compromise the security of protocol or even simulate it with purely classical resources. And in quantum sensing also, like the big research line there is actually to understand like how we could counteract the fact that noisy measurements are like dumping this precision. Like in principle, if our measurements are noisy, classical estimation might end up being more economical. So this is about noise, but then we also have a problem of adversarial activities. So in quantum computing, for example, like how do we see this is that like the problem is how can we know that we are actually using quantum computer and that indeed classical resources are not responsible for computational process. So how can we know that it's actually quantum resources, something that is not simulable quantumly, responsible for the computation process, or that some adversary is not just trying to trick us by providing us some classical resources that are computing. So in the immediate future also, like, well, we are likely not to have really just everybody quantum computer, but it's supposed to be some cloud computing. And then the question is, well, how can we preserve this secrecy of our computation? Because like the problems that we want to solve with quantum computers are likely those that involve some level of secrecy that we would like to preserve, like our computation secret. In quantum communication, like, well, especially in quantum cryptography, all protocols are defined by taking into account some eavesdropper. So eavesdropper might corrupt quantum systems to steal the information or use the imperfections of our sources or measurement devices. So like in principle, if we are paranoid, or well, in principle in cryptography, we want to make sure that our key is secret, even if eavesdropper is plotting with the equipment provider. So we would like to avoid all these situations where somehow adversarial activities can hinder our protocols. And for that, in that aspect, like certification of quantum resources is very important. So in certification, somehow we want to make sure that the apple is okay to eat. So like in this fairy tale with Snow White, that she had this apple that was poisoned but looked good, like, so somehow like it would be good if she could somehow certify beforehand that this apple is not damaging. So this is about certification. And then when we talk about certification, well, we want to certify that we are using actually quantum resources, and there somehow, well, we have to start from somewhere our certification. We have to make some assumptions about our system. And somehow the number and quality of these assumptions is it acts in different direction than quality of certification. So more assumptions we make about the underlying system, our certification is weaker. So for example, if you would like to certify that we have a dragon, it depends from where we will start and what will be the starting point of our certification. So if our assumption is that the dragon is anything that is a reptile and that breathes fire, well, then we could try to see the tail and see the breathing fire. But in that case, there could be a lizard that is blowing some candle and that could actually like pose as a dragon. So clearly, like, we have to somehow set the smallest possible number of assumptions about our quantum system if we want our certification to be good and trustworthy. So in this aspect, we are coming to the concept of device independence. So I will explain a bit more about this. I don't know if you had some talks about this already, but so somehow device independence means if you want to make a certification that does not depend on the devices we are using, on their properties. In some sense, it is a black box certification. So the question there is, can we ever certify quantumness without making absolutely any assumptions about underlying system? So if we have some experiments like that supposedly produces entangled states, we are performing some measurements, like, can we do certification if we treat all the devices that are present in our experiment as black boxes, that we have no idea about their inner functioning? So in this sense, like usually in certification, like, or verification, we have some verifier that is verifying that something is functioning properly. So we want this verifier to be completely classical and don't want to give him any quantum powers. So this is somehow intrinsically related a bit to also some philosophical questions, like that is, can we really trust our senses? So in general, we are gaining our knowledge through our senses. Our senses are somehow all the time making measurements, like we are seeing the things and that is a measurement, we are hearing a thing, that is some kind of a measurement. But then how much can we really trust our senses? Like if we are making parallel that like our senses are making certification, what if we cannot trust our senses? What if we cannot trust the tools for certification? And this is related to this in Western philosophy famous question that was asked, like, what can we know about the outside world, about the world in general, if there is some evil demon that is controlling either our senses or the external reality, and thus giving us some false view of the world, like false information. So, like, this question was posed by French philosopher René Descartes, and it established this concept of Cartesian methodological doubt that was very important for developing the whole modern philosophy and development also of science in Western world. So if you would like to have this, to apply this Cartesian methodological doubt to our means of gathering information, like then in classical physics, like this is very difficult, because classical physics requires trust, because gaining any knowledge requires a perfectly characterized measurements, and this is related to the fact that information can be copied arbitrarily many times without being disturbed. So classical physics cannot really pass this Cartesian doubt test. But in quantum physics, there is one theorem that probably you all heard about, that finds a good use in certification, and that is no cloning theorem. So in no cloning theorem says that in quantum physics, information exists as a unique, and making copy necessarily destroys the original. So we cannot really copy quantum information. This no cloning theorem is related to the principle of monogamy of quantum correlations. So and you know that like one particle can be maximally entangled with just one other particle, and then they would be isolated from the rest of the world. So, but what is interesting for us is that these quantum correlations that are related to this non-cloning, they have a classical footprint, and that is non-locality of measurements correlations. So if you apply some measurements on entangled states, I will talk more about this, like they will see some correlations that are stronger than classical. And in this way, like trusting only classical labels that are telling us which measurements to perform, and abandoning any trust in quantum operation allows us to gain knowledge about quantum properties of the underlying system. So, well, this is related to important question like that somehow lies maybe even in the heart of our quantum information theory, like this paradox from almost 100 years ago of Einstein, Podolsky, and Rosen. So like they published this paper in which, well, in my interpretation, like the problem that they were not, that was puzzling them, and in the first place, Einstein, was that there exists some inherent randomness in quantum theory. So because there is this inherent randomness in quantum theory, like that we somehow, that could be removed only if we accept some spooky action at distance, how they were called it. Like then EPR postulated, Einstein, Podolsky, and Rosen postulated that quantum theory is not complete theory. So this theory has to be completed with some hidden variables, which should be described by the completion of quantum theory. And then if we would describe this hidden variable, then we would remove randomness, which seems to be inherent to quantum theory. So then, well, this somehow problem of hidden variables, like as posed in the seminal EPR paper, like was difficult to falsify. So somehow one would say that it didn't even belong to the realm of scientific theories until like, well, 60 years ago we had this Bell's theorem. So John Bell was interested in this EPR problem, and he started from two principles. So one was the principles of relativity, so that like information cannot be transmitted instantaneously. And then there was this principle of objectiveness of reality. I don't know, like people call it in different ways. Like there is, first time I learned about it, we were calling it counterfactual definiteness. And this is a principle that the observables have clear defined values independent of the measurement process. So this was related to this fact that whether moon exists when we don't watch it, or whether like tree that falls in a forest like produces any sound if nobody is listening, and so on. So Bell started from these two principles and saying, okay, like let's see what is the properties of a theory that satisfy both of these principles. And then he managed to prove that all theories satisfying both principles, principle A of relativity and B of counterfactual definiteness, allow for only limited correlations between distant particles. So more specifically, the results of measurements performed in distant laboratories can be correlated only up to a certain degree. In other words, they must satisfy Bell inequalities. So that holds for theories that satisfy these two principles. And then, so I don't know if, yep. So this created, somehow this opened the way to actually test in laboratory, like, or scientifically test, like, whether our world can be described with a theory that satisfies these both principles. And this important concept, there are these Bell tests. So in Bell tests, we usually have two agents, Alice and Bob. Like, we could have more if you want, but in the simplest case, it's two that are Alice and Bob. Like, they are spatially separated, they are not communicating, and they receive some classical inputs, Alice X and Bob Y, and they are supposed to return some classical outputs, Alice A and Bob B. So, and in quantum theory, like, well, they would use these classical inputs to choose which quantum measurements to perform, and the measurement result would be just their classical output. So now Bell test is characterized by the set of correlation probabilities. So this joint conditional probability to obtain A be given X, Y. And then, like, we could somehow measure correlations present in these probabilities. So in quantum theory, and we could see if it violates Bell inequality. So in quantum theory, like, basically, like, we would model measurements of Alice by M, A given X. So for every X, it's different measurements. A defines an effect. Measurements of Bob would be M, B given Y. They would share some quantum state rho. And then these probabilities that characterize the Bell test would be given by the Born rule, like, that is first class of quantum theory. And then, like, this Bell inequality, basically we could see it as a functional of these probabilities. And, like, this local bound is the bound that satisfy correlations that can be obtained in any theory satisfying these two principles. So now theories satisfying these two principles, like, we call them local hidden variable theories, and, like, they have these local hidden variable models. So in local hidden variable models, like, probability, full probability, not conditional, to obtain to have outputs A and B and inputs X and Y would be given by, there is this hidden variable lambda that Bob and Alice have access to. This is some type of randomness. Like, then we have P lambda, and then we have this probability that X and Y given lambda, and at the end probability of obtaining outputs A and B given X, Y, and lambda. Now, if we assume that this condition of measurement independence, that is, that somehow inputs to the Bell test are freely chosen, randomly chosen, they cannot depend on the hidden variable that Alice and Bob have access to, then this conditional probability, like, breaks, and we have just P of X, Y. And then we have this locality principle, and that is that in this theories, like, output of Alice cannot depend on the input on Bob. It could depend only on input of Alice and the hidden variable, and the same holds for the output of Bob. So, and indeed, in that case, like, if we take these two conditions, we could get our conditional probabilities that have this form that, for all of you that know a bit about Bell test, like, this is familiar thing. So that this probability is D lambda, P of lambda, and then probability of A given X lambda times probability of having B given Y lambda. So then somehow, well, this mathematically looking at these things, like, we could see these correlation sets geometrically. So then, like, we could form a set of all these correlation probabilities, or we call them behaviors, like, that are compatible with local hidden variable models, and this set is a polytope. So polytope is somehow defined with finitely many vertices, like these extremal points, and set of quantum correlations. So this is the set of correlations that could be obtained by Born rule, like, is actually larger than this local set or polytope of local correlations, and it itself, it's not polytope. So in this geometrical structure, Bell inequality is simply a hyperplane that is separating local set from quantum set, and non-local correlations are those that lie outside of the local polytope. So now the simplest example of Bell inequalities is CHSH inequality. Like Bell inequality, well, they are a way to test if our nature is locally causal. They are, as I said, functionals of correlation probabilities. And then in the simple scenario where we have Alice and Bob, like, their inputs are bits and their outputs are bits, then we could define Alice's observables and Bob's observables. We define these expectation values, and then the famous CHSH inequality is A0 B0 plus A0 B1 plus A1 B0 minus A1 B1. It's less than 2. So 2 is local bound. But if we have a quantum strategy, then Alice and Bob could share maximal entangled state. They would perform these observables like that are anti-commuting, and they would obtain quantum violation to square root of 2. So well, last year Nobel Prize on Physics was actually awarded for the experimental violation of the Bell inequalities. But now we want to see like how all these that I said, maybe all of you know this, and I don't know if it was too slow, but like this was introduction to certifying different quantum resources. So how can this non-locality help us certify different resources? So one first resource that we would like to certify is quantum entanglement. So, well, you know that entangled state is the one that is not separable. So, and usually like how do we certify entanglement is by using entanglement witnesses. So entanglement witness is a operator that satisfies 2 properties. So one is that it is positive on all separable states, and it is negative on a target entangled state. So for every entangled state, there is some witness operator that is negative on it, but positive on all separable states. So this is the geometrical structure, geometrical figure. So this W here is a valid witness operator for all states that are on the right side of it. But on the left side, there are some entangled states that would be not detected with this operator. But then this V prime is not valid because you see like there is this state that is separable that violates the witness. But then, for example, for a maximal entangled state, like for a singlet state, the witness would look like this. And then like the problem with witnesses is actually that we have to perform these measurements. So like in Pauli basis, for example, for singlet, and these measurements have to be completely characterized. But from what I was saying before, we would like to do it in a device-independent manner. And then, like, well, let's see what is happening with the Bell inequalities if you have separable states. So definition of separable state is that, well, it is just integral over product of states. And then, like, if you have these correlation probabilities given by Born rule, and if you plug in it this separable state, like the resulting correlation probabilities will be local, or they're compatible with local hidden variable models. So that means that separable states cannot violate Bell inequalities. And that means that if we violate Bell inequality, that is a device-independent witness of entanglement. So somehow we don't even need to trust what did we measure. We don't need to trust what was the system. Like we'll have a device-independent entanglement witness. So the next resource that we would like to certify in this device-independent manner is randomness. So somehow, well, genuine randomness is very important. And like, well, what does it mean to be random? Like usually we say that something is random if it is unpredictable. But unpredictable for whom? The question is like, and then like we would like that something is really random if it is unpredictable for everyone obeying the laws of physics. And then like, well, classical randomness that is used a lot today, like it comes from difficulty to solve equations with many unknown variables, or from ignorance about the system. So for example, our atmosphere is very complex systems. We cannot really solve exactly the equations, and thus predicting exactly like the weather conditions, exactly, it is a bit of a random process. So, but then, like if you say that someone with all possible knowledge or an all-powerful computer maybe would be able to predict these processes. So, like then there was this idea of using quantum theory for producing randomness. And then one way is like, for example, you know that if you measure a state which is linear superposition, it would give us a random result. So if you measure in computational basis. But if the measurement devices are not trusted, so we are in this black box scenario, the measurement statistics violating Bell inequalities, but then correlations violating Bell inequalities, they cannot be simulated classically, because nobody can predict measurement results as they are non-existent prior to the measurement. This is like the falsehood of the second principle in Bell's theorem. So this somehow leads to the concept of device-independent certified randomness. So if we violate Bell inequality, we will know that there is some randomness in the results, and there are different processes like related to randomness. One is generation. So this will be obtaining randomness from scratch. If you don't have any randomness, and then like we need to produce it. So this is very difficult to do because input for Bell test have to be random. Like it is like in this equation like that I had here. Like this means that inputs are random. If they're not random, then Bell violation does not certify any randomness. So somehow generating randomness from scratch is not impossible in black box scenario, like if you don't have already some. But then there is this process of randomness amplification, where if we have some initial randomness, even though it is imperfect, it can be amplified or extended through a Bell test. So like for device independent certified randomness, we can like the way how we do it is that we violate Bell inequality, and then based on the Bell inequality violation, like by using different techniques, we can determine the power of the adversary that is trying to guess the outputs. And then we have to relate violation of Bell inequality with the entropy of local or global outputs. So this is already something that is almost 15 years like rolling, and like important first experimental demonstration was this one published in Nature like already 13 years ago. So there was also like some that is that was more like, let's say, powerful against more powerful adversaries. That was done a few years ago. So then we can go to see how we could do device-independent secret key distribution. In secret key distribution, Alice and Bob want to exchange the key they use to encrypt and decrypt messages they are exchanging. So the key needs to remain unknown to some adversary, hacker, whatever. And like, as I said, classical cryptography relies on encryption procedures. We rely on the assumptions that some problems are difficult to solve. This is computational security. But in quantum key distribution, like if Alice and Bob maximally violate the CHSH inequality, they know that an adversary Eve cannot know the result of their measurements. So the measurement results can be used then as the key. But in here, like for example, like if they want to have the key, they need to perform measurements that both outputs of Alice and Bob will be the same. So it is not the case for the CHSH measurements, because there Alice applies sigma x, sigma y, and Bob different measurements. But then Bob can just add another measurements to the CHSH that is anti-parallel to one of Alice's measurements, and they could create key in this way. So then the standard way for device-independent quantum key distribution would be like our favorite step: violate Bell inequality, find the relation between the violation and quantum bit error rate. But then so this could be problematic because of losses, and somehow device-independent quantum key distribution is difficult to implement. So we have some important step towards there, as this paper did published last year in Nature with trapped ions. So then further, like we could talk about, if we want to resource that we want to certify would be quantum dimension. So, and in this case, this aspect, we could talk about dimension witnesses, as system dimension is a very valuable resource for many quantum information protocols. So for example, for randomness amplification, if we have a larger local system, then we could perform measurements with more outputs, and this will be more random. But then system dimension is not something that is measurable quantity. Like it is in quantum dimension, like we talk about dimension of the Hilbert space. But in quantum theory, exactly this lower bound on the dimension of the underlying Hilbert space can be witnessed in a device-independent manner. So the key for this is that certain type of inequalities like can be violated more by the system of higher dimension. So we know that, for example, there is this type of inequalities that was published in this paper by Brunner et al. So if we have qubits, we could achieve some violation, but if we have qubits, we could achieve higher violation. So if we see violation that is in between, like bound for qubits and bound for qubits, we could know in a device-independent manner without trusting anything that we have something more than a qubit in our system. And well, this was also like done in experiments in this science paper by the group of Bristol, if I'm not mistaken. So then, like I could pass to device independent or trust-free verification of computation. So well, this is maybe the most tricky part. Like when we talk about verifiable quantum computation, because it is a big and important problem. How can we verify that a given machine is quantum computer, that it relies on quantum resources to perform computational process? So like there are three ways how in general we think we could do it. So one is ask it to solve a problem with clear separation between time needed for classical and quantum solution. Then we could ask it to do some sampling problem that I believe to be difficult for classical computer, like boson sampling. And then there is the second, the third way is to perform an interactive proof. So interactive proof, like is a well way that like some computer that can solve problems for some complexity class can solve, but those with less power cannot. And if the device passes the interactive proof, it could convince us that it can solve problems from this class. So like these first two methods would not guarantee that we actually have quantum computation, like because, well, for the first we don't have actually any provable separation. We only have guesses or like somehow conjectures. And the same thing is for B. Like we actually it would not be black and white, like black and white proof that we are having quantum computer. But then performing this interactive proof is actually the best way to verify quantum quantum computing. So, and well, I just told a bit, but let's explain more what are these interactive proofs. So in computational complexity theory, interactive proof system is an abstract machine that models computation as the exchange messages between two parties, a prover and a verifier. So prover is a machine that can perform computation, and verifier is interacting with it and trying to verify that this machine can do computation. So the interactive proof for quantum computing, so like quantum computers can solve problems for complexity class BQP. So interactive proof usually in this case, like verifier would like to make sure that prover can solve any problem from this class BQP. And it is usually reduces to a problem of certifying that quantum computer uses particular quantum state and performs particular measurements which are together universal for quantum computing. So prover needs to convince verifier that it can prepare any efficiently preparable quantum state and perform measurements on it that are universal for quantum computing. So this is also related to the concept of somehow delegated quantum computing, like these research lines are somehow like intertwined. So in delegated computation, the computational process is delegated by a computationally bounded verifier. So that would be a classical verifier that can do some classical processes to one or multiple provers that are supposedly quantum machines. And then in some rounds of the interactive proof would serve to verify quantumness. So in some rounds, like the verifier would convince themselves that prover is quantum. And in the other rounds, like verifier would ask prover to solve a problem. So only then, if these rounds that where quantumness is verified are passed, like then we could know that our quantum computation is correct. So this process makes sense if the prover cannot really distinguish rounds in which it is asked to convince the prover in its power from the rounds in which it is asked to compute. So, and this delegated computing is sometimes desirable to be blind, so the provers should not know which problem the verifier is solving. So in this multi-prover interactive proof, like usually there is verifier and several non-communicating provers that aim to convince the verifier that they can perform universal quantum computing. So they can do this by proving they share quantum resources, and this usually this proof relies on Bell non-locality. Now using somehow non-locality for this computational problems, like there are several mathematical and computational problems where like the solution is relying on violation of Bell inequalities. So this is I will not go into details because I still have some things to tell you, like the most important, but these are serial sum problem, Cons embedding theorem, or like, well, this important complexity result that class of problems solvable with the multi-prover interactive proof where provers can share entanglement is basically the same as all recursively enumerable problems. So these are all the basically solvable problems. We could discuss it later if you have a question. So, but now for all these things, like to verify somehow that we have quantumness through Bell and locality, to verify that we have quantum state, the most important method is self-testing. So theoretical formulation of self-testing is as follows. So we have Born rule that provides us a way to calculate correlation probabilities if we know the state and measurement. So we have state and measurements, and then these correlation probabilities are obtained by Born rule. And then self-testing aims to find inverse relation when possible. So if we have access to these correlation probabilities, we would like to get knowledge about which quantum experiments led to these correlations. So in this sense, self-testing can be seen as a map between the set of measurements correlations and quantum experiments. So in practical meaning, like, because we are talking about the black box certification, like Bell inequality violation can be seen as a device-independent witness of entanglement and incompatibility. But then maximal Bell inequality violation could be seen as a device-independent witness of particular quantum states and measurements. So somehow, if from the correlation probabilities I could learn what were the state and measurements, like then this indicates my certification procedure. Okay, and then to formulate the problem, like we need to introduce some notation. So one is that we have in our Bell scenario, in our black box scenario, we have some experiments that involves untrusted source and untrusted measurements. Like this, we call physical experiments. Like we could model it with some unknown state living in a Hilbert space of unknown dimension and local measurements applied by Alice and Bob. And then we have this ideal experiment that we want to make sure that we are having there. That is a specification of the source and measurements. This is the reference measurements. So our aim is then to find the relation between the physical and reference experiment if physical experiment reproduces some correlations. So now how far can we go in learning like this reference experiment? Like this is related to the limits of self-testing. So here we draw a conclusion only from the correlation probabilities. And thus there is no way to verify exactly the state, as there are always some set of transformations which can have correlation probabilities unchanged. So if you have experiment involving a state and the measurements, like then if we locally rotate state, measurements, and the state, like then we'll have probability distribution, correlation probability unchanged. Also, like our state can have some additional degrees of freedom on which measurements act trivially, like this would also leave correlation probabilities unchanged. So then that means that we could like somehow locally rotate our bases, then add additional degrees of freedom, then together all these locally rotate and so on. So these two transformations are known as under the concepts of local isometries. So some of the best way we could do to compare like physical state and reference state is to ensure that they are related through local isometries. Okay, so and then to return to our CHSH inequality, like indeed it was proven like 30 years ago that maximal violation of CHSH inequality is a self-test. So maximal violation of CHSH inequality implies that Alice's and Bob's measurements anti-commute, and then through some mathematical like arguments, like we could actually make sign of equality between anti-commuting pair of observables and the qubit subspace. And then when we know that Alice and Bob are having qubit subspace, like from the maximal violation, we could ensure that they must have also maximally entangled pair of qubits. So this is a simplest possible self-test. Then the first self-testing paper appeared, well, it was more 2004, but the spirit of that was already in this 1998 by Myers and Yao. And in the last 2 decades, there was a significant progress was made in understanding how we could self-test certain classes of states. So we know how to self-test all pure bipartite states, all multipartite GHZ states, all multipartite decay states, all graph states. But then the question that remains in this device-independent or black box certification of states remains whether can we self-test all pure entangled states. So finding these self-testing correlations for an arbitrary pure entangled state is very challenging problem. So like, if I have time, I will make some comment on this. But then I was saying just about self-testing of states, but we could also self-test measurements. So for example, instead of certifying the presence of specific state, one could try to certify presence of specific measurement. And again, this measurement can be self-tested only up to local isometry. So I could find this isometry that is somehow mapping my physical measurement to my reference measurements. And then the maximal violation of CHSH inequality implies that Alice and Bob's measurement anti-commute. And then every anti-commuting pair of observables is isometric to Pauli's sigma z and sigma x. So further, like one result that we had a few years ago is that we could do other things to self-test. So instead of self-testing a particular state, one might be interested to show that a state that produces some correlations belongs to certain entangled subspace. So entangled subspaces are subspaces consisting only of entangled states, and they are very useful for error correction because, like, these entangled subspaces are basically error correction codes. And like Stein code, Shor code, Tori code, they all use these entangled subspaces. So in this paper, like, we show that it is possible to build Bell inequalities which are maximally violated only if states belong to a certain entangled subspace, or in the other way, if this state is a code that could be used as a code for error correction. So, well, here is just a representation of a toric code, but we wouldn't have time to go into many details. Well, then another question that is related to this self-testing as black box certification is robustness, because it is very difficult to exactly reproduce the required set of correlations or to maximally evaluate some Bell inequality. So there is always this noise and the coherence. So can we say something about the physical state and measurements if they almost violate the CHSH inequality or violates it to some degree? So if we can do this, we say that there is robust self-testing. And because I don't have much time, I don't need to go through this definition, but in principle, like, somehow I would like to make connection between the state reaching violation B and its fidelity to maximal entangled state for CHSH inequality or target state that maximally violates some other inequality. So this is a very difficult task, and in general, we always know that we could get some small bounds, but like there is a lot of effort like to improve the methods for robust self-testing. There are numerical searches that rely on the approximation of quantum set. And then, well, there is because I was all the time telling about self-testing as a map from this set of correlations to set of quantum experiments. But this is somehow a theoretical concept, like in this paper that was published in PRX Quantum, like, we're actually connecting this self-testing as a theoretical map from set of correlations to quantum state with actually a device-independent state certification. So the question is, like, well, what kind of device-independent state certification we need? So in one sense, we need it to be a protocol. So protocol, it means that there are instructions. Okay, do this, do that. Like, if you get this result, then you have the state. So somehow when we phrase self-testing, like, if it reproduces some correlation probabilities, but how do we learn these correlation probabilities? This is not a protocol. Then we want our certification to be sample efficient. So we don't want to just need enormous amounts of copies of the state to certify that we have a good state. We don't want to waste like a lot of resources. And then we also want our certification, like, ideally that it is non-IID. So somehow that our source is not in every round sending the identical copies. And then we would also like it to be, well, I named it DI, so it would be like to be device independent. And we would also like that it is certificate. So somehow, like, in the standard, like, these self-testing descriptions, like, we have to measure all copies, obtain these correlation probabilities, and then we know that the state that gave correlation probabilities was something. But in that case, we already measured all the states, we already destroyed them all, so there is nothing we could use for some further protocols. So in this sense, we would like to have certificates so that we measure just some subset of copies and we could say something about the rest. So, well, in this reference here, like, we actually start from self-testing protocols and build a device-independent certification that has all these properties that are satisfied. So, well, I told you about a bunch of results related to device-independent certification of quantum resources, and well, I hope that there was some interesting information that could that you would like to learn more about, or that you could like to explore further, like regarding the self-testing, like well, there was in 2020 with a colleague from now he works in Xanadu, we wrote a review on self-testing of quantum systems. So like if you want more information about it and usefulness of self-testing for certification, you could check that paper. And then, well, I also had some results about network self-testing, but I think that I saw that Tony Yassin, if he already gave a talk, he told something about that, and that is our result for self-testing all pure entangled states. So I would not go there because I think I already passed my limit of 45 minutes. So I would stop here, and if you have some questions, I'm happy to answer.
So the floor is open for questions. Actually, so you have said that in a system dimension is an important factor.
Yes.
So, but the examples of the state you have mentioned there, as far as I see, all of them are discrete dimensional.
Yes.
So, are you planning to extend that in continuous variable, and how, like, will that give an advantage or disadvantage?
Yes, well, okay, so somehow for the purely practical applications, like you might want to talk about that, and so in this sense, from some simple Bell inequalities, like we don't really have these results defined for continuous variables, and well, also like just the process of Bell non-locality, like, or Bell violations for continuous variables, it's very complicated. But I mean, there are results that are important somehow theoretically, where we want to separate that we have finite dimension from having infinite dimension, like, and like there are some results, and there are some results actually related to Bell inequalities or some type of correlations that could be reproduced only if we have a system of infinite dimension and not finite.
Thank you. So any other questions from the audience?
I have questions. Can I ask?
Yes.
Yeah. Thank you for your talk. First question is, could you please name the problems where device dependent are preferable as compared to device independent?
Well, so somehow, if you want to think about some practical implementation where you would like to work with device dependent, and I don't know exactly if I understand the question. So if you want to say when it is preferable, I mean, in general, if we want to convince that we have some amount of randomness, or we want to extract a key, if we are device dependent, that means that we have characterized devices, characterized measurements, and we will usually extract a longer key, we'll have more randomness. So in that sense, it is better to have device dependent, but then it might compromise security. So if you want to use, when you can use device dependent, like I would be, you could use it well when you are somehow absolutely sure, like at how your functions divide, how your functions, how your devices function, sorry. So if you have fully characterized measurements, like it might be an overkill to go to do something that is device independent if you really know, like how things in your lab function. But in general, like these device independent things are important for, are very important when we don't have this characterization of measurements, or we don't have trust in them, that is mostly related to some adversarial scenario like cryptographic or so on.
Mm-hmm. So am I correct that a random key generator for key distribution device, it is device dependent, because this generator should be with all the legitimate participants,
So
as compared to key distribution based on quantum entanglement?
So, but what was the first thing that you said, that it is device, which protocol is device dependent?
If we are going to share key distribution, so it's for key distribution, we can use random key generator. We can use entanglement,
Yes.
E91 protocol. So in case of, I think, and when you are sharing your key by using quantum entanglement, it is device independent as compared to.
Yes, it could be made device independent. It could also be device dependent, like, because somehow, well, the way how ACAT protocol, for example, was defined, like it was defined, I would say, as device dependent, but it was like somehow also like in its spirit, it was very easy to make it device independent. So, but yeah, in general, like if you want to do something that is device independent, like you have to use entanglement. If you don't have entanglement, like then we don't know for the device independent protocols that would have this information theoretic security. Like if you don't have entanglement, you would have to use some cryptographic procedure and rely on some computational security, like of your protocol.
So that was my first question, because here I just wanted to know what applications or problems where we can use device dependent and where we can't use device dependent. So, but in case of quantum entanglement based quantum cryptography, we have less speed as compared to random key generator. So, okay. So second question is there any recipe or algorithm which can be used to build witness operator?
So you mean entanglement witness operator?
Yes.
So, well, I'm not, I never really worked in details on these things, but I guess that there are quite some recipes, like there are these review of Ottfried Güne and Geza Todt, like I think that they have, there's some systematic ways like to do it, but then I never worked really much on entanglement theory and these things, so I cannot really say for sure yes or no, but I mean, for at least for the entangled states that appear that are relevant for us, let's say, that have some nice structure that are useful for quantum information, like I guess that they're, for all of them we know how to build witness.
Thank you.
You're welcome.
So any other question?
If there are no more questions, can I ask one more question? Sorry.
Yes.
Yeah. So what is the trend in the market when you do the certification? What kind of certifications you do usually? I mean, what is the trend?
What is sorry, I didn't answer.
Trend.
Trend.
Yes.
But for what? Certification for what?
For certification.
Of states, of, I don't know.
Of algorithms, or maybe devices, or something, or maybe software. So maybe you know what is the trend? Trend I mean that maybe you are doing certification for random key generator. Maybe you are doing more on key distribution based on quantum entanglement. So what is the trend right now?
Well, I don't know. I think that, I mean, I from what I understand and what I know, I wouldn't say that there is definitely one trend. Like, I think there are people that are trying to do these things with entangled states and somehow in the device independent manner. But then there is also still like people that are building protocols that are in some sense semi-device independent, that are based on prepare and measure scenario, where you don't use entanglement. But so it somehow really depends on what you want to use it for and what type of security you need. I cannot really say that I'm observing some clear trend, but I think that there are somehow different directions that are all developing, and they are all useful for some purposes. Like, just depends for what you care about.
Thank you.
You're welcome.
Any other question? So if not, let us thank the speaker. Thank you, Dr. Supic.
Okay, thank you for inviting me. And well, I mean, if you have some questions or want to know something more, you can find, I guess, my email somewhere on internet, so you can write. Thank you.
Sure, thank you.